I guess we'll start. Good afternoon, everyone. It's a pleasure to have Professor Stan Metchev as our speaker today. Stan and I have known each other for a while. I first met him in one of the Astronomical Society of New York meeting held in Rochester, New York. I think it was 2009. He had just taken up a position at Sony's Stony Brook. But since then, we have been in touch on and off. So it's a pleasure to host him today for the colloquium. A brief bio of Stan's. He did his bachelor's from Harvard University and then PhD from Caltech. After which he moved to UCLA, University of California, Los Angeles for his postdoc. In 2008, he took up the position of assistant professor in State University of New York, Stony Brook. And in 2013, he moved to where he is currently at Western University of Canada. So Stan, besides his research, he's also currently the chair of the Science Advisory Committee of the 30-meter telescope and also the co-chair of the Canadian Space Agency. Not agency, Space Committee. Yeah, sorry. And Stan's research interest has always been on very low mass stars and substellar objects, so objects which cannot burn hydrogen in their core, which we call them brown dwarfs, and exoplanets. So today he is going to talk about very interesting results that has just come out from JWST, namely the detection of dust in brown dwarf substellar atmospheres of substellar objects, brown dwarfs and exoplanets. These are silicate dust. For the first time, we unambiguously were able to detect the signatures of silicate dust in the atmospheres of exoplanets and brown dwarfs. Let's hear more about this from Stan. Stan, all yours.
Thank you, Manoj. Thank you for the promotion. I've never been called the chair or the co-chair of the Canadian Space Agency. I'm not sure I won the position of the promotion, but I'll clarify that I'm the co-chair of the Joint Committee for Space Astronomy. I only have an advisory role. I make no decisions. I'm happy in those roles, advisories without decisions. I try to avoid decisions as much as I can. But anyway, it's really a pleasure to come visit the Tata Institute for Fundamental Research. I have never been here before. It's really only my second visit to India after a 30-meter telescope meeting about, I think, 9 years ago. But Manoj reminded me that we actually do know each other for quite a while, 2009, and he was at the University of Rochester at the time. He was a postdoc. I think it was his first postdoc right after his PhD at IIA. And I remember meeting this young man. We had a very deep discussion about Spitzer infrared spectra of young stellar objects. He was clearly much more into that field than I was. I was learning a lot from him at the time. So there was a big and very sort of constructive, positive impression that I had from him, and I'm glad that we've managed to keep in touch. And I had the pleasure of meeting a fantastic group of PhD students that he has today. Makes me very envious. But anyway, I really appreciate the invitation. So I'll be telling you today about research that my team and collaborators are doing. It's on dust, clouds, and brown dwarfs, and how we came up with a sort of an idea as a shoot off from that research to look for habitable exoplanets. And I'll tell you how this happened. I come from the University of Western Ontario, which we like to call Western University. And because Western University is so generic, we always have to say Canada. But then you look at Canada, Western University is not really west of much. Let me see if I can figure out how to advance, actually. Oh, this. I am actually stuck with the remote advancer, aren't I? Oh, here we go. Oh, okay, yes, perfect. I got it. Thank you. Thank you. All right, so Western University is in the city of London, on the River Thames, believe it or not, but in Ontario. Nowhere near as glamorous as London, UK, but we're still 500,000 people, which is a biggish city in Canada, halfway between Toronto and Detroit. The university itself is sizable for Canadian standards. It's about 25,000 undergraduate students and a few thousand graduates. And it's really Western Ontario because of historical reasons. This was the western part of Canada back when Canada was being founded. We have one of the biggest programs in physics and astronomy in Canada, specifically in astronomy. We have 12 faculty members in astronomy and astrophysics, and then a few other sort of areas of strength, planetary and atmospheric physics being one of them. And these are the kinds of things that we do in astronomy. This, by the way, is our building on a nice autumn day. It's already covered under snow by now. It's nice to come here to warm weather. This is one of my students at the controls of the Gemini South Telescope when we're using the Gemini Planet Imager. So the high contrast imager for looking for extrasolar planets through imaging. And this is my team at our local observatory in Ontario, where we built 3 robotic telescopes that are each half a meter for altogether different kind of astronomy that I'm not even going to talk about today, but it's sort of given our team some experience in doing some astronomical instrumentation, building things. Western also hosts the Western, I will say Western, it's Western University or the University of Western Ontario, hosts the Western Space Institute or the Institute for Earth and Space Exploration. And so astronomy is really just one part of the kind of research that we do there. We also focus on some sort of small sat development, space and remote health. So Canada is a vast country. It's hard to cover it with proper health services, especially in the remote areas. So we're actually doing some leading research in robotic health or remote health. So through sort of contraptions that allow physicians to actually intervene remotely, and it's potentially of use also for astronauts in space, having the position on Earth. There's some analog tests and missions that we do on terrain that is sufficiently foreign that it could as well be on the moon, and Canada has lots of those kinds of terrains as well, and so forth. But coming back to dust clouds, brown dwarfs, and extrasolar planets, and why we care. Dust clouds, so these are literally condensate clouds, but now made of silicate dusts, not water. These are the only kinds of clouds that we can, I'm going to use this, that we can study directly in worlds outside the solar system. So in the solar system, the planets, we see all sorts of other chemical clouds, starting with water clouds on Earth. But if we go outside the solar system, the only kinds of clouds that we can actually study directly, chemically, are made of dust. And we'll see why. Brown dwarfs themselves, so this kind of object that is a really good proxy for what extrasolar planets look like. They have similar types of atmospheres, but they're brighter. So they're easier for us to study. And as we'll see toward the end, brown dwarfs and their sort of somewhat slightly more massive counterpart, which is very low mass stars, they may actually offer the fastest path to finding habitable, inhabited, not just habitable, inhabited extrasolar planets. So they may give us the best opportunity to actually discover life in the next decade. So what are brown dwarfs? This is a cartoon that shows to scale the sun in this corner, and then a low mass star called an M-type star. And then there's Jupiter here at this end. And then there's these 3 kinds of objects, and we call them spectral types, L, T, and Y. How many non-physicists are there in the audience? Everybody's a physicist or an astrophysicist. Okay. I'm going to go harder on you then. Do we have non-astronomers? Okay. All right. Okay. Oh, okay. Okay. All right. Okay. Great. Fantastic. But you've heard about spectral types of stars, presumably, possibly. Okay. Yes. So brown dwarfs span 3 spectral types, L, T, and Y. And this is really entirely determined by actually spectral appearance, but more or less temperature, like in stars. And the coldest ones, the coldest one that is currently known is actually Earth's temperature, about 270 degrees Kelvin. Colder than Earth, really. Earth on average is a little bit warmer than that. So they get to temperatures down as low as Jupiter. You can also see they're similar sizes to Jupiter. This is actually true to scale picture. And that's because they're all supported by degeneracy pressure in their interiors. They're not like stars, which are supported by radiative pressure or convective, like M dwarfs. I mean, they're fully convective, but the supporting mechanism is degeneracy pressure. In addition to the brown dwarfs, I'll also use this term called ultra-cool dwarfs, which spans these three spectral types, but also includes sort of a small portion of the coolest of the M-type stars. So objects that are less than about 2,700 Kelvin in temperature are known as ultra-cool dwarfs. And all ultra-cool dwarfs, again, tend to be about Jupiter size. They're degeneracy pressure supported. So why are they good proxies for extrasolar planets, other than the fact that they're about the same size as a giant planet? Well, at the very low temperatures, the various molecules in their atmospheres will start condensing. So they actually form layers of clouds like we see on planets with atmospheres in the solar system. So if you start with the warmest of these ultra-cool dwarfs, the very late M's, or maybe even the early L-type brown dwarfs, you form this cloud layer of one of the most refractory kinds of condensates. So you have sort of calcium titanium oxides, or known as corundum. And that's one cloud layer you have maybe at high altitude at the proper, basically, pressure temperature point for condensation of this cloud. You go to a cooler object, an L-type brown dwarf. This same cloud has now sunk to a lower altitude because that's where the pressure and temperature are appropriate for condensation of this kind of refractory element. But then higher up, you have a different kind of slightly less refractory cloud. And now it's silicates or magnesium iron clouds. Magnesium silicates or iron clouds. And then you go cooler still, T dwarfs, the same thing happens. This most refractory cloud is deep below the visible atmosphere. And then you have starting to build this layer cake of clouds in the atmosphere. And then you go down to Jupiter. This cloud is still there, just completely invisible. And we always see is the tops of ammonium and ammonia hydrosulfide in Jupiter. So brown dwarfs basically tell us how this happens. And solar system planets are here, but extrasolar planets actually inhabit this sort of entire temperature range. But brown dwarfs are brighter, they're slightly more massive, so we can actually study these clouds better. And in this, today I'll just be talking about these silicate clouds because, again, they're the only ones for which we've been able to actually see the chemical signature. The other ones we still can't see the chemical signature of. But these ones have a very prominent silicate absorption at mid-infrared wavelengths, which those of you who actually do, for example, James Webb analysis of spectra know about these silicate absorptions. And brown dwarfs are not, they're not just some exotic object, they're actually very common. If you look at the closest neighbors of the sun, and there's basically 7 individual stars here, 4 stellar systems. Of these 7 individual stellar objects, 3 are brown dwarfs. The nearest Proxima Centauri is, the nearest is Proxima Centauri, it's a late M-type star. Alpha Centauri is a double, so this actually counts as 3 stars altogether, all stars. And then there's Barnard star, which is the next closest stellar system, now known to have extrasolar planets. And then you go a little bit further out, you have 3 brown dwarfs. So they don't quite make up half of the stellar population, just so happens that we have some very nearby, but they're a very common member of the Milky Way galactic population. Sorry, what is the what distance?
Distance is like Proxima Centauri distant line.
Oh, this is I borrowed this diagram from some NASA website. I think this was when it was actually measured by parallax. So parallax being the sort of trigonometric estimate of the how far an object is based on how we see it at different sides of the orbital position of the Earth around the sun. So this, okay, that's when the distances were measured. Yes. Yeah.
But it's the whole light year. So others are, that's the whole light year.
Yeah, this is.
That is 1976 light year.
This is the year when the distance was measured.
distance is the 1.5 times, then this angle will be the same, but the nearly same. And 1917, 1916, but the distance are different. So opening angle will be the different.
Yeah, so this is, I mean, they're in completely different parts of the sky. So the distances from measured just, this is basically when photographic plates came a little bit earlier, but this is when astrometry was being able, consistently be done with photographic plates, I suppose.
I noticed that some of the nearest stars are all white, so this is the wide field infrared survey fluid.
Correct.
That's a very, I mean, in the last 15 years or so.
Correct. Yes, you notice.
Because these are very dim stars that only recently we saw them, even though they're very nearby.
Correct. Yes, that's a very good point. Thank you. So you notice the names start with Y. This is the Wide Field Infrared Sky Explorer survey. And these objects were, you see the distance 2013, 2014, that's when they were discovered. So even though they're, part of the 7 closest stars, they were discovered just over a decade ago because it's so intrinsically faint and apparently dim as well. This one is actually pretty bright, but because it's so nearby, and this one too, it moves across the sky so fast that it's actually hard to find it in different catalogs in the same place, which is part of the reason they were not found. They were just moving so quickly across the sky that they were not in the same place at different catalogs. All right, so before we actually were able to measure the chemical composition of clouds and brown dwarfs, there was plenty of indirect evidence they exist. So the strongest evidence that started being collected sort of about a decade and a half ago was the fact that these brown dwarfs, all objects spin, and if they have clouds, those clouds they may form storm systems, which would then appear to create inhomogeneities on the surface or in the top of the atmosphere. So when you have an inhomogeneity and the object is spinning, you'd expect a change in the integrated brightness. And that was this signature that was seen convincingly for the first time. The speculation and some tentative observations existed even before that, but for the first time convincingly demonstrated in this sort of relatively bright early T-type brown dwarf in the late 2000s. And what you see here is this variation on a constant period of 2.4 hours. So this is the spin period of the object, 2.4 hours, pretty quick, so 10 times faster than the Earth. And the brightness amplitude is about 0.5% peak to peak. And for reference, there is a normal star here in the same field of view of the telescope showing no variation. So kind of demonstrating these variations are real. And what's happening here, if I borrow my favorite brown dwarf as an example, calling Jupiter my favorite brown dwarf, is, we have these kinds of storm systems, these atmospheric storms, the Great Red Spot being the most well-known one. And Jupiter spins around its axis every 10 hours, so 4 times slower than the brown dwarf I was telling you about. But as it spins and these various storm systems come in and out of view, the integrated brightness of Jupiter changes just by a bit. And with a sensitive enough photometry, you can actually see this. So if you were to say observe Jupiter at a wavelength of about 400 nanometers in the blue, this is now a longitudinal map of Jupiter. You can see how the brightness actually changes. This is now integrated brightness of the surface at each longitude. And there's about 1% variation. And that's all you see. It's about 1%. So your eye is not going to be able to see this. But with a sensitive enough photometry, you can do this. And now, interestingly, if you look at a different wavelength, Jupiter looks differently. So now at 9 micron wavelength in the mid-infrared, you see this sort of double-peaked feature. You'd be forgiven to think that actually Jupiter spins twice as fast if you're looking at that wavelength. But this is now, again, integrated brightness at 9 microns at each longitude. And the features that dominate this brightness curve here are these bright bands near the equator. And the features that dominate this light curve are the in-between two dark regions. They're actually bright in the mid-infrared because you're seeing through in between the cloud layers. So Jupiter shows this variation rotationally, and we had some demonstration that a brown dwarf does that too. But this was sort of the late 2000s. This was sort of the beginning of this sort of study of clouds and weather, if you will, outside the solar system. There was an interesting study done, in fact, on this nearest pair of brown dwarfs that were discovered in 2013. Oh, is that a question? Yeah, go ahead.
Is it rotating, like there's a double peak rotation? Is it because different layers are rotating at different speed? Or is it there is some other reason?
That's a good question. Is it because the different layers are rotating at different speed? That's why we get a double peak. Actually, this is just purely a integration along the vertical longitude. So it just happens that the brightness here is kind of integrates to the same thing as the brightness here. Yeah, there are two brightness peaks on the surface, actually. Okay. But it's true that the different layers, and I'll go to that a little bit later, it's true that different layers, actually even in the reference frame of Jupiter, they actually appear to be moving in opposite directions because they're in different hemispheres, in the opposite hemispheres. Yeah. So there was an interesting study done on this nearest pair of brown dwarfs, a Doppler spectroscopy study. We can actually not only monitor the rotation period, but also spectroscopically be able to see whether there's any bright or dark spots at very high dispersion spectroscopy, very high signal to noise. And this was actually a map of the surface of this nearest, one of the two nearest brown dwarfs. This was published in 2014. And this is sort of the first resolved map. It's sort of very crude resolution, but longitudinally sufficient sensitivity to see there's dark spots and bright spots. And this was the nearest brown dwarf. Now, if you're an astronomer, you say, the brightest object or the nearest object displays some behavior. Basically, everything else in the universe has the same behavior, right? That's how astronomers work. This is our null hypothesis. And with this null hypothesis, we basically ran 4 large programs on the Spitzer Space Telescope when it was still operational. This was sort of in the mid 2010s. And with the original One Weather and Other Worlds, our goal was to see, do really all brown dwarfs have these giant stores on them like the Great Red Spot? So simple questions. Do all brown dwarfs have great red spots on them? Our advantage with using a space telescope that works in the infrared was that we have a 10 times better precision in measurements than we can do from the ground. We're also observing in the infrared where brown dwarfs are, because they're cool there, their brightness peaks there. And the result was very simple. The answer was yes. Literally, statistically speaking, 100% of brown dwarfs actually show, they should show variations, depending on how we look at them, viewing geometry. Because if we look at them pole on, we're not going to see rotational modulation. But accounting for this, we could actually infer that 100% of them should show these variations. And there was a very neat follow-on result, which now comes back to in a little bit to the question that was just asked. We studied one of these brown dwarfs then jointly with Hubble Space Telescope and Spitzer. And you can see the brightness variation here that's measured by the Spitzer Space Telescope in the mid-infrared. And you can see that sometimes it has these high oscillations and sometimes it's sort of relatively flat. And the reason is, and this is sort of our inversion of the light curve onto a 2D surface now of the brown dwarf. The reason is that you have these 2 bright bands in the northern and southern hemisphere of this object, and they appear to rotate at different angular velocities when you integrate the light. So when they combine constructively, you have these large oscillations in the light curve. When they combine destructively, you have more or less a flat light curve. So if you were to actually place yourself now in the rotational frame of the brown dwarf, this is what actually looks like. You have this southern hemisphere rotating here to the west and the northern hemisphere rotating to the east. And then when these 2 bright bands line up, that's when you have a peak in the light curve. And there's also actually evidence for a storm somewhere on the surface. We can't tell exactly where it is, so we've placed it there in our map, but somewhere there's a giant storm as well. And so these are basically caused by longitudinal waves. atmospheric waves around the object. So this, yeah, question.
What is the great red spot analog?
What is the great red spot analog? In what do you mean?
I mean, in your previous slide, you said everything should have a great red spot.
Oh yeah, so yeah, this will be the great red spot analog here. Yes, yeah.
So I imagine that that hypothesis could be stated in such a way it's trivially always true in the sense you can always find the hottest spot in an image, and then so do you have some more stringent criteria saying the great red spot has to be brighter than the rest by a certain fraction or something like that?
The answer is no. We initially were just looking for variations that would give us the fact that it's in homogeneities, and homogeneities will reflect temperature differences on the surface.
So
But
your claim that all should have greatest spot, it is actually a trivial claim that there is always a hottest spot.
there's always there's some temperature difference. That's really what it is. And it's also not in a way that the temperature differences are multiple and spotted, in which case they'll sort of wash out. But there's actually some sort of larger dimensionality. So that's why we say it's probably more like a big storm. Yeah.
So what is the difference in temperature?
So the difference actually turns out to be very small. It's only a few Kelvin. Yeah, it's surprisingly small. We thought it would be more like 50 or 60, but it can be as little as a few Kelvin. Yeah, but it ends up, because of how the radiative transfer works, I see your question. It ends up actually producing a noticeable change in the flux. The question in the back, yeah?
I maybe do not know this, but like what is the reason for the bands in the northern and southern hemisphere to move in opposite directions?
Why are they spinning in the opposite direction?
Yeah.
Because they're in opposite hemispheres. So now we're dealing with the Coriolis effect.
Just Coriolis.
Yeah,
That's the only reason.
yeah. And then the Hadley cells that actually, so the atmospheric term here on Earth, you have three different layers in each, three different zones in each hemisphere that actually will have opposite rotation. So and the two hemispheres are opposite of each other. Should the what?
It's gas and outwards. It's affected by Coriolis.
The which force? The
Coriolis.
yes, yeah.
The gas in northern hemisphere and
Right, yeah. So the Coriolis effect will, to first order create these kinds of storms. But if you actually integrate it over the whole surface of a spherical rotating object, you end up creating bands, longitudinal bands. And we have 3 of those bands in each hemisphere on Earth. And it's purely a Coriolis force-driven differentiation. And as a result, hurricanes they can basically go from one band to another. They'll change sort of direction in which they go as a result. They'll first go in the northern hemisphere, they'll go east to west. And then if they jump to the northern band, they'll go sort of west to east. So this picture is we're already talking about planetary Hadley cells. This is basically what we see on Jupiter too. In Jupiter, because of its faster rotation than the Earth, we actually have more of these bands, not just 3 in each hemisphere. We have, I think, about 6. So that's why we have more of these horizontal bands on Jupiter. But this is, mid-infrared artist's rendition of a rotating brown dwarf, mid-infrared actual observation of Jupiter. So this was, at this point, pretty strong indirect evidence that we have these atmospheric inhomogeneities that are like clouds. And so summarizing the results from all these programs, we could find these spots, clouds, storms. We could actually not indirectly, but also get rotation periods as an ancillary result to this. And some of them can be as fast as 1 hour, objects that are basically flying apart almost. We could even measure the dominant pressure levels where the clouds reside because we had measurements at different wavelengths. So we can do sort of crude tomography of the atmosphere. And even with polarimetry measurements on ground-based telescopes, we could infer that the largest oscillations in the brightness would happen at wavelengths around 1 micron. Polarimetrically, we could see this. So that was sort of giving us an idea that the dominant particle size in these clouds is probably about 1 micron. And so far, again, this is all indirect evidence. And then came our direct observations of the chemistry of the clouds. So again, with the Spitzer Space Telescope in the mid-2000s, there was some evidence that some of these L-type brown dwarfs, or the warmer type brown dwarfs, show this sort of dip in brightness around the 10 micron range. So there's one here, this sort of square, rectangular region, I should say, indicates where this dip in brightness is inferred compared to other objects that don't seem to show anything like this. And so two different publications on some overlapping objects were showing this. But the Spitzer Space Telescope was decommissioned shortly after these observations. I should say the spectroscopic mode of Spitzer was decommissioned. The cryogen ran out. And then we were left hanging with the question of why do some objects show these and why do some others don't? They're all the same sort of spectral type, which if you're a star means you have more or less identical properties. But for whatever reason, for brown dwarfs, some have this absorption, some don't. And all of these L-type brown dwarfs are expected to have these silicate clouds. So why do some of them show silicate cloud absorption, some don't? So then with a former postdoc, we decided to look at the entire archival data from the Spitzer Space Telescope, all of the spectra that were collected of brown dwarfs. And so there were 101 such spectra, about half of which were published, sort of the higher signal to noise pick. And then the remainder were unpublished. And so there were mostly low signal to noise data left, but there was a few nice high signal to noise observations that were still not published. And so with Spitzer spectroscopy sort of being decommissioned with the cryogen of the Space Telescope running out in 2009, we were not able to do this again until James Webb 12 years later. So when we were doing this, we're sort of trying to prepare for James Webb. So we looked at all the Spitzer spectra. This is just an extraction of some, mostly low signal to noise. But then we could sort of notice that around this 10 micron region, some objects, again, show this absorption, and some of these were not even published, and some of them don't. But again, the data are quite noisy. So when you have noisy data and you want to extract a signal, what you do is you average down the noisy data with all your independent observations and try to get something that's slightly higher signal to noise. And also we decided to just define what we call just an integrated flux over where we expect the silicate absorption to be. So we created an index of the silicate absorption strength at around 9 microns. And then we plotted the strength of this index, which is really the difference between the sort of flat line here and the depth of the absorption. We plotted the strength of this index as a function of the spectral type of these stars and brown dwarfs. So warmer objects, cooler objects. And if there's no absorption from silicates, we expect this sort of relationship here, this decreasing line. But you see there's a very clear bump with lots of noisy measurements, but taken as an ensemble, they're very significant detection of silicate absorption. And virtually, the average brown dwarf basically shows something, and there's some that show a little less, and some that show a little bit more. So this kind of illustrated the fact that we still have this conundrum. Why are some supposedly cloudy brown dwarfs showing very little in terms of silicate absorption, where some of them have a lot of it? And that's where we come back to this picture that we had with these longitudinal bands that we found with the earlier observations with Spitzer. If you look at Jupiter from the equator, it looks like this. If you look at the poles, you're not seeing these bright regions. You're seeing something maybe somewhat different. So it's possible that what we're seeing here with these differences in the appearances of the spectra of brown dwarfs is that we're actually seeing maybe an inclination effect, because we don't know what the inclinations of these objects are. An inclination is not something that we measure when we observe a star. We measure brightness, we measure spectra, we measure projected rotation and things like that, but not the inclination. So if we can measure the projected rotational velocity, and you can also estimate or calculate the true rotational velocity, then we can actually estimate the projection angle or the inclination. So we can back out the inclination that way. The sign of the inclination angle is, this is our projected rotational velocity, this is the actual velocity. The actual velocity, if you know what the rotational period and the radius, you can figure out what it is. The projected rotational velocity is something that you can measure with high dispersion spectra. So we measure the projected rotational velocity V sin I from high dispersion spectroscopy from the Doppler broadening of the spectral lines. This is the kind of, for example, instrumentation work that's being done here at TIFR, building spectrographs for telescopes to do this kind of work. The rotation periods, well, we actually found these out in our program to discover weather. This rotation period just sort of came out of that equation. The modulation happens on the rotation period. And then the radius, if you know the distance to the object and the luminosity and temperature, you can just figure out what the radius is from the Stefan-Boltzmann law. So combining all this, our light curves from the Spitzer Space Telescope that show variations on very short time scales or very long time scales or very even longer time scales. We have the rotation periods. Then we have this factor covered. We have P rod. And then for this, we need high dispersion spectroscopy. And that's what a high dispersion spectrum of a brown dwarf may look like. These are observations. The red curve is an observed spectrum in the near red part. The blue curve is a model of what the atmosphere at this temperature should look like. And as you can see, they look nothing like each other. These are our residuals here on the bottom. But the caveat here is that the model is a very slowly spinning brown dwarf, like 5 kilometers per second only at the equator. Now, when you start spinning this model up, we'll have Doppler broadening of the absorption lines. And you'll see it actually, if you spin it up, it ends up converging onto the data. So this is actually a very rapidly spinning brown dwarf at an equatorial velocity of 90 kilometers per second. Is that a question?
Yeah, a big notice. The y-axis is also a wavelength, normalized wavelength, and then I didn't understand what this is.
Oh, you caught a typo in my plot. It is normalized flux. It's not normalized wavelength. I am so sorry. I've been using this for goodness. Oh my goodness. This is normalized flux for sure, not wavelength. Yeah, this is wavelength on the x-axis. Yeah, thank you. So an astronomer will just look at a spot that do not even read the axes, and they'll just say, but it's good to have physicists to catch when the astronomers sort of talk.
Absorption is a CO.
It's carbon monoxide, yes. Yeah, so it's actually our best measure really of rotation in brown dwarfs because it's such a prominent comb of absorption lines. So using this, we can measure the projected rotational velocity. We know the period, so then the radius we can estimate. Well, the radius is another one of those things that are actually very hard to measure because these objects are small, they're far away. We need a telescope beyond the size of anything that we have to actually physically resolve the surface. But these are all brown dwarfs. They're all 1 Jupiter radius, more or less, give or take, 10% plus or minus. We can do a little bit better than just that rough estimate, 0th order, but they're basically 1 Jupiter in size. So then, given all this, we can actually get these spin axis inclinations. So putting these things together, our measurements of the strength of the silicate absorption and now the known orientations of the spin axes, we discovered a very, very clean, very neat, and very sort of unknown previously relationship that objects that have more silicate absorption, that have more clouds, are seen closer to equator on. So 90-degree inclination means you're looking at the equator, and objects that are less cloudy are seen at inclinations that are much closer to pole on. And mind you, with our approach, we cannot measure inclinations of like less than 20 degrees. Because we would need to see variations and kind of Doppler broadening that we just can't measure with our instrument. So we kind of limit it to something upwards of 20 degrees. So for the data that we can gather, this correlation is very evident. And it's interesting, there's also a color coding of the data here. This is the redness of the apparent spectrum in the near infrared. So if you're seeing a dustier object, it should also be more reddened. And that's exactly what's happening. These darker colored data points are redder. They're not just cloudier because they have more silicate absorption in the mid-infrared. Their overall colors are redder, as you would expect. So then we created a cartoon for our press release. You know, the different objects that we see. Here is one that's seen almost close to the pole on, and here's another one that's seen almost on the equator. And if you look at what their spectra look like, it's exactly as you would think. The one that's seen on the equator, the red one, you see this very sort of rising slope from shorter wavelengths to longer wavelengths. This is a red spectrum. The one that's seen almost at the pole, you see a sort of more declining spectrum, you know, roughly here across the near infrared. So this is a bluer spectrum. So equator on red, pole on blue. And anywhere in between, you have the range of colors. So now this is very much akin to an issue that was being faced by the active galactic nuclei crowd in the 90s. You have different ways to classify active galactic nuclei based on their observed properties. And in the late 90s, there was this unified model that was proposed that said, actually, the entire difference that you see in these AGN observations stems from the viewing geometry. And if you're looking at them from sort of edge on onto the equatorial torus, which is very dusty, you infer sort of one kind of object. And then if you look closer to the pole of the orbital configuration, you see a different kind of object. And so with brown dwarfs, we're actually having this unification model moment about 20 years or 30 years after the AGN, after it was discovered in AGN. All right, so we have direct evidence for these clouds, and can we actually say something now about their composition? The silicate feature in the mid-infrared is very broad, but it's also sensitive to what the clouds are actually made of. And things that can vary are sort of your magnesium and iron content in the silicates. And if you have more magnesium, you have the peak of the absorption sort of to longer wavelengths. This is all theoretical models. And if you have more iron, you should be seeing more absorption in the shorter wavelengths. And this is where our James Webb observations come in. So we did a survey of brown dwarfs with James Webb, now much higher signal-to-noise data, much better than the Spitzer. These are, you know, L and T-type objects. In the L-type objects, we very clearly see these these silicate absorption signatures. And one thing that we can see, we have enough sort of diversity at similar types of brown dwarfs, we can actually compare how they look. And very neat thing to see, if you subtract what the continuum looks like, and you look only at the at the silicate absorption, identical objects, same spectral type, show this sort of change in central wavelength of the absorption and in strength. This almost looks like an inverted sort of Wien displacement law, if you will, in a black body. It's nothing to do with this, but it just kind of looks like that. And again, this is governed by how much magnesium you have in the silicates or how much versus iron. And so this is entirely, for example, enstatite, whereas this is iron-rich enstatite here. So not forsterite, not a forsterite, iron-rich forsterite. Iron-rich enstatite. Sorry? Yeah, it is asymmetric, yes. The absorption is asymmetric, yes. It is not it's not an atomic line. This is very broad over multiple microns. Yeah, it's amorphous dust, so you'll create a continuum of absorptions.
The microstructure in that curve, you know, the small things are much less than 1 micron. Is that physical, or is it a plotting artifact, or is it a digitization artifact?
This is noise here. This may be something. We haven't explored in that kind of detail yet. But this is where the data become noisy. Yeah, you have a good eye. So now we've feel like we rule inclinations of brown dwarfs. Inclinations are us. We know how to do that. So then we thought, well, we can actually make further use of this and optimize a search for exoplanets. Now we know how to determine inclinations of brown dwarfs and actually low mass stars, and they all have the same radius, so we can actually get their inclinations very easily. We can optimize searches for exoplanets around this kind of object. And really we're looking sort of a step ahead. We want to find, so these kinds of hosts could reveal Earth-sized planets. And if these Earth-sized planets are in the habitable zone, they would be the ones that we actually be able to explore for the signatures of atmospheric signatures of life with tools that we currently have in space, the James Webb Space Telescope. So this is the sort of the bigger challenge. So the easiest technique for discovering exoplanets is this transit method. Basically, I think my animation stopped here. You wait for a planet in fortuitous alignment so the planet is oriented such that it crosses in front of you. And if you have a Jupiter-sized planet around a sun-like star, the signature is about 1% change in brightness of the star. Then the next thing is you want to characterize the atmosphere. So you do that with observations of the transit at different wavelengths. And so that's how you can infer whether if you're observing in the water band, you have a deeper transit. If you're observing in the methane band, you have a maybe intermediate transit. And if you're observing at a continuum band, when there's no molecular absorption, the transit is the shallowest. It basically tells you how large the planet appears in front of the star. So this is transit spectroscopy. It's sort of a crude measurement, but it gives us a molecular composition of the atmosphere. And that's sort of at a factor of about 100 sort of finer resolution than you need than just to detect the transit itself. But that's still doable, 100 parts per million, and we can do that with the James Webb Space Telescope. The thing is that then you want to be looking for the telltale disequilibrium signature of life, and that's difference in transit's depth that reveal ozone and methane in combination. That's in principle a combustive combination that should not exist if the atmosphere is in equilibrium. So if we look for this, if we find this, it's sort of a good signature that a good indication of life may be producing the oxygen and the methane, or at least one of them. Except that these kinds of sort of Jupiter-sized planets around sun-like stars, they don't really have biochem. They're not suitable hosts for life. If you want to look at Earth-sized planets around sun-like stars, now the transit depth is much smaller, 80 ppm. It will be impossible to find an atmosphere around those because now the precision required is less than 1 ppm, and we cannot do this with James Webb. So this will be the best target as an Earth analog, but we can't do anything about the biochemistry. However, if we look at one of these kinds of hosts that are much smaller than the sun, the transit depth of an Earth-sized planet is now a full percent versus the less than 0.01% around a sun. And these objects, by the way, I showed you they're some of the most common objects in the galaxy, brown dwarfs and and very low mass stars. Jointly with if you go to mid-type M dwarfs, you have about 3/4 of all stars in the galaxy in this population bin. So it's highly numerous. They're also known from the few planetary systems known around these kinds of objects. They're known to host numerous rich systems of rocky planets, but few of them are known just because these objects tend to be faint. So they're too faint for them to be revealed in surveys en masse. But if we're able to find planetary systems around those, an Earth-sized planet now is back to this comfortable 1% transit depth, which gives us sort of a relatively comfortable and achievable atmospheric depth measurement with James Webb. And now we can meaningfully answer the question, is there life on these planets? Because this measurement is now within the capabilities that we have. All right, so let's maybe focus on these ultra-cool dwarfs and brown dwarfs. But transit surveys are notoriously inefficient. The probability of having transiting geometry is maybe 1 to 3%. And you want to find these kinds of planetary systems that will be edge on and not focus on these that are pole on that you'll never see. And how do you select these ones? Well, you select the stars that you see almost at their equator. You just basically eliminate the stars that are spinning near pole on as viewed from you. You pre-select your stellar sample to optimize it for the transiting systems. So we're back to this approach. Measure the projected rotation. Yeah, question.
Is it always the case that the spinning axis of a star is perpendicular to the disk of the planet?
Yes, very good question. Is the invariable plane of the planetary system similar to the orbital plane of the planets? For planetary systems with multiple planets, yes. For planetary systems with one known planet only, or maybe two, not necessarily the case. But for multiple planets, yes. And in the solar system, yes.
This is it's an absolute statement or something, the statistical majority.
It's in my extra slides, yes, but it's actually a measured correlation. Yeah, very good, very good question. Yes. So we're back to this. So now we do photometric periods and mass. We use things like TESS to find the photometric periods of ultra cool dwarfs because they're in the TESS all sky survey, and then the really challenging and difficult part is to measure these rotational velocities. That's a lot of telescope observations on 4-meter class telescopes or larger. So now we're about halfway through a sample of about 1,000 objects. We've been collecting these data for the past 3 years, aiming to maybe complete this within a couple of years. And the fact that they all have about the Jupiter radius gives us the inclination. So we want to basically create a very clean sample of single brown or ultra cool dwarfs that are seen close to their equator to look for rocky planets. Those actually that would be then potentially characterizable for the signatures of life. The tool to detect these planetary systems does not really exist yet. I mean, yes, James Webb can certainly find them, but nobody's going to give us 2 years of time on the James Webb Space Telescope to maybe produce a few planets with unknown frequency yet, which is why we are basically building our own space mission to do this, or proposing our own space mission to do this. It's called the Photometric Observations of Exoplanet Transits mission, POET. It's a 60 by 60 by 60 box with a 20-centimeter telescope and infrared capability. And it's a collaboration between 2 lead universities in Canada, but we are actually a number of more institutions are involved in it. It was identified as a top priority in our long-range plan for astronomy for this decade, and would be our 3rd space astronomy mission in Canada. Which is when we present this to the government, they say, "Okay, this is big stuff." And these are sort of what the parameters of it look like. The 20-centimeter telescope will actually have 3 bands starting from near UV to near infrared, and this will be simultaneous. We have 2 beam splitters that will actually give us all these data simultaneously. And so one of the 2 main science goals is to find these Earth-like analogs. And then another one is just characterizing atmospheres of known bigger exoplanets, which is where the near UV band actually comes in. And there's actually significance for multi-wavelength astronomy too, in particular for following up transients, and other kinds of stellar astrophysics. And another thing that we sort of allowed us to dip our feet into instrumentation a little bit is that these infrared cameras are not well characterized for space use yet for astronomy. So we've started a technology readiness levels, a ladder program to validate their use in space. So we just launched a balloon this last summer with one of these cameras to see how they behave in the stratosphere for astronomical observations. So this was our first attempt at a balloon launch with the Canadian Space Agency, and we have at least one or 2 more planned to further validate the cameras for space use. And this is where I'm actually interested in talking to the balloon program that you have here at TIFR as well. So this is where I'll end. And I'll actually just sort of summarize the main outcomes of this research. Clouds are the only kind of extrasolar cloud that we can see directly. They are telling us that the atmospheres of brown dwarfs actually have a very strong longitudinal dependence. And James Webb now is allowing us to reveal the mineralogy of the clouds, something that has not been done before at all with any kind of cloud outside the solar system. And we are now using these techniques to optimize a search for habitable exoplanets with a proposed space mission. Thank you.
Thank you, Stan. We'll take questions now. I'll take Stan.
I'm just wondering, so is there any comparison was done with like resemblance with the Neptune? Of course, you have a general variation, temperature variations, and then you have multiple rotation period where you are seeing cloud coverage. So, of course, you are saying template with Jupiter, but any attempt was seen for the Neptune also to just to compare? Of course, you will not see silicate there, but ice clouds. So.
Oh, on solar system planets? Okay, yeah. So yes, it's some work has been done on the light curves of the solar system planets to actually see the variations in the chemistry. There's not that many sort of planet as an integrated light observation. I know there's some actually being done here for the sun to see how the sun, integrated light from the sun behaves like. But for planets, it just has not really been done. They tend to saturate in WISE images from the WISE survey, so it's hard to actually tell what the infrared signature is. And the planetary scientists, they'll look about, care about this individual storm and that individual band. So yes, the data are there; they exist. They've just not quite been done.
So in high energy astronomy, we are often interested in these things we call molecular clouds. They're near supernova remnants and they serve as like a beam dump for cosmic. Is that the same thing as a dust cloud?
The molecular clouds in the interstellar medium would not be the same as a dust cloud. So the dust is actually condensates.
Sorry?
The dust cloud is a condensate cloud. It forms from condensation of the dust grains into a cloud.
But they're called giant molecular clouds. They're different from this.
They'll be different. Those will be basically individual. Well, I guess there are some bigger dusty molecules. They can be a few microns, but
Yeah. They're very different. This is the cloud and
okay, but if that's the case, then what do you mean by the statement dust clouds are the only kind of extrasolar clouds? Because giant molecular clouds are also detected, and we know something about their chemistry and stuff.
I'm calling extrasolar cloud as a shorthand of clouds on extrasolar worlds, or like on planets, or like on compact objects
within the thing.
On compact objects in atmospheres. Yes.
Okay.
Yeah.
Sense.
Yeah.
More questions? Questions, comments?
I noticed in the geological spectra of the silicate absorption, the mineralogy looks more or less amorphous. So is it that the crystallization is getting destroyed by some process in these objects, or is it inherently amorphous? And does it then affect how sort of that, like what type of planet will form around this type of spectral type of star?
So you're talking about the variability or the spectral signature being amorphous?
Spectral signature here, like this looks like more or less mostly amorphous silicate.
It is all amorphous, yeah.
Yes. So like, is there some process? Like, why don't we see crystalline silicate absorption here?
Why don't we see? Yeah. So crystalline. So to form crystalline silicates, you need very, very slow cooling. Here we have. If anything, the heat loss rate is faster than what you'd require for silicate formation, for crystalline silicate formation. In addition, you have convection, so continuous sort of collisions among these dust molecules, which will destroy crystalline structure, at least in my understanding. We're sort of at the beginning stages of figuring out why this happens.
Yeah, but these are brown dwarfs, so it's mostly the atmosphere also probably came from the interstellar cloud. So normally, these are not formed in the protoplanetary. This where some crystallization has happened.
Yeah, this will be secondary dust in some sense, if you will. Yeah.
More questions? Yeah.
So I was wondering, as with inclination angle, this absorption feature has a correlation. Will another a third axis would be like evolutionary stage so that we see cloud in one evolutionary stage and disappears in the next. Can that happen?
Yeah, that's a good question. Actually, I'll show an earlier plot, maybe to help myself in answering this. This one. Yeah, so L and T dwarfs are actually kind of an evolutionary sequence, right? Brown dwarfs will form hot, and then they'll cool forever because they don't have thermonuclear reactions. So this is sort of an evolutionary sequence. Maybe not like exactly linear in the spectral type differentiation, but it is an evolutionary sequence. So you can see that in the beginning you don't have them, and then at the end they disappear. So there is an age, there is a time axis, certainly. In this case, it's sort of covariant with the spectral type, more or less. Yeah.
So if we don't see cloud, it can be either inclination effect or
yes. So yeah, if we don't see a cloud, it may be an inclination effect, which is what we think these green dots do. They don't have much of an apparent cloud, or it's just too cold. It's a T dwarf. And here the cloud is there. It is just below the visible photosphere.
Any more questions? If not, let's thank Stan again. And let's move over to the West Canteen Terrace for tea and snacks. So you can interact with them over tea as well.